All right, in this one, you're using our rules of exponents here. So remember, 234 to the 0 power, anything to the 0 power always equals 1. So this one, well, is a 1. That's it. Okay, anything to the 0 power is 1. If I look at the next guy, remember negative exponents just send me to the other side of the fraction bar. Keep in mind, though, when you see something like this, that -3, that exponent only applies to the y. All right, which means right now this is a fraction like over 1. But since that negative exponent only applies to the y, the only thing I move is the y value, and that gives me a positive exponent. The 7 itself, well, that had nothing to do with that negative exponent. That one stays where it is, okay? So only the thing with the negative exponent flips to the other side of the fraction bar, all right? If I look at this one, I have some multiplication. When I look at the numbers out front, I know how to multiply regular old numbers. -4 times 7 is a -28. But now when I'm multiplying, I actually add the exponents. That's the special rule that we have for exponents, okay? So the numbers out front work the same way they always have, but exponents are always doing something special. So here, that's going to be a to the 11th power. I add the exponents, okay? If I look at the next one, once again, a fraction bar is a division sign. It's saying, hey, 24 divided by 6. I know how to do that one. 24 divided by 6 is a 4. But now the special rules for exponents is that when I'm dividing, I subtract the exponents. So that's going to be an x to the 10th, okay? And then this one, if I raise it to a power, again, if you ignore the variable, if I just had 3 raised to the 2nd power, well, that 3 squared, that's a 9. It's 3 times 3, all right? But now the exponents have a special rule. When I raise it to a power, I multiply the exponents. So that's going to be h to the 8th power. Okay, so again, rules of exponents. Exponents are always doing something different. So whatever the operation is, all right, I treat the numbers the same way I've always treated them, but then I use my special rule for exponents, all right? One of the places where we use rules of exponents quite a bit is in scientific notation. So just a quick refresher on scientific notation. If I have something like this guy, the first example I'm going to rewrite in scientific notation. The second example I'm going to rewrite in standard form, just going back and forth between these two things. So this first one, 2,560,000, that's written in standard form. I'm going to write it in scientific notation. And so remember, I basically just moved the decimal here. And so the decimal's right here. I just move it to a place that gives me a value between 1 and 10. And so right here, I just move it 1, 2, 3, 4, 5, 6 spaces to put myself there. And the reason, once again, that I put it there is because the number out front in scientific notation, all right, has to be bigger than 1 or bigger than or equal to 1, but it has to be less than 10. It has to be a single-digit number with decimals, okay? And so I put that decimal in between the 2 and the 5. And again, if I count up how many spaces I moved it, well, that just becomes the exponent of my 10. So it's 2.56 times 10 to the 6th power, because I moved the decimal 6 places. And just remember, if I move the decimal 6 places in this direction, that's a positive 6. It's expressing a bigger number. To express decimals, if I had a really small decimal and I was moving the decimal point the other way, then I might use a negative value. And so that's what we come to when I look at this next one. That negative value is telling me which way to move this thing. So if I took this thing, the 3.2, off to the side and said, hey, oh, sorry, let me give myself a little more space here. I want to move this thing 6 places, but I want to move it 6 places to the left when I do this, because the negative symbol, if this was a positive, yeah, I'd move it to the right and I'd get a really big number. But a negative gives me a decimal, so I go 1, 2, 3, 4, 5, 6. And notice I kept moving even though there weren't values there. I just put zeros in those spots. And then my decimal point goes here. And so if I kind of clean this up a little bit, I've got point. Looks like I had 5 zeros, and then the 3, and then the 2. And that's this thing written in standard form, okay? So remember, negatives always give me really small decimals, and that should help tell us which way to move. Positive always give me really big values. That should tell me which way to move, okay? And then using rules of exponents in conjunction with scientific notation, we just do the same thing we've been doing. So I divide the numbers out front, or I multiply the numbers out front. Those always do the same thing, but my exponents this time are part of the 10. And so I apply rules of exponents to the 10 raised to whatever power. So for example, if I look at this one, the 8 divided by 2, right here, this front piece where I have the 8 and the 2, that reacts the same way that's always acted. So 8 divided by 2 is a 4. But now when I deal with these, the second half of this thing, the thing that has the exponents, well, I'm just going to leave the 10 the way it is as a 10. And now I'm just going to apply rule of exponents. When I divide, I subtract the exponents. So 5 minus a negative 4, and if you need to take that off to the side, it's 5 minus a negative 4. Remember, that's like adding the opposite. So that's going to be a 9. Okay? And this is in scientific notation. The 4 is okay. That's the other thing I have to check. If this guy isn't the right kind of value for scientific notation, I need to change it. Okay? But that one looks good. All right? If I look at the next one, same kind of thing, except now I'm multiplying. Well, I treat the numbers out front the same way I always have. I do 2.5 times the 7, and grab a calculator for this. So, punch it in, 2.5 times 7. That gives me a 17.5. But now the exponent part, the thing with the 10, I leave the 10 the way it is. Rules of exponents, when I multiply, I add the exponents. That's an 11. Okay? But now this one's not quite right. I got to adjust it a little bit. See, because this number isn't written properly for scientific notation, I actually need to move the decimal one more spot. So I'm going to rewrite this as 1.75. And since I moved it one more spot, that 11 is going to become a 12. Okay? But again, we use scientific notation in science quite a bit, and when we're dealing with large and small numbers, we can make simplifying values in scientific notation easier by applying rules of exponents. And then these guys simplifying each of these roots. Remember, with the numbers inside, there are two ways that you can do this, so I'll do this one twice. We can do our factor tree where we just start splitting this thing up into any multiplication we can think of. So that's like 2 times 26. And, you can use a calculator to assist you. And that's 2 times 13. And then remember, I always extend this branch so I can see it all written side by side. And now to take the square root, I look for pairs. Here's a pair of 2's. So since I found a pair of 2's, I put a 2 on the outside of the radical. And since this guy doesn't have a pair, he stays inside the radicals. He stays under the square root. Okay? And then applying the same thing, but with our different rule. So here's option number 2. Option number 2 is we look for perfect squares. Remember our list of perfect square numbers, like 2 squared is 4, 9, 16, 25, 36, 49. Okay? And that list goes on and on and on. I don't know how many you know. All right? But I can take the square root of each of those, like here, the square root of 4 is a 2, the square root of 9 is a 3, the square root of 16 is a 4, okay? So basically what I do is I say, hey, let's break this 52 down into values that I know how to take the square root of. And so 52 is actually 4 times 13. It might take a little bit of guess and check. Just start guessing values from this list up here until you find one that divides nicely into the 52. And so I find out that 52 is the same thing as 4 times 13. But now I know how to take the square root of 4. The square root of 4 gives me a 2. So I can write a 2 down. And then when I try to take the square root of 13, the square root of 13 I don't know how to do. So I leave it as the square root of 13. That's the other option. Okay? Same thing with the next guy. Again, I can do the factor tree. I'll do the factor tree first. Maybe do something like 2 times 24. And then this guy, that's 2 times 12. And then that's 2 times 6. And then that's 2 times 3. And so again, clean this up a little bit, extend each of these branches so I can see everything written side by side. And now look for pairs. Here's a pair of 2's, so I put a 2 on the outside. Here's another pair of 2's, so I put another 2 on the outside, and it's all multiplication. And then this guy doesn't have a pair, so he stays on the inside. So it's going to be a 4 root 3. Okay? Again, if I applied the other version of this thing, option number 2, I look for values from that list up there, and the biggest value, and that's kind of the important thing, is I want to find the biggest value from that list. The biggest value from that list is 16. So it's 16 times 3. The square root of 16 is a 4. But the square root of 3, I don't know, so I just leave it as the square root of 3. Okay? I get the same value. All right? Just two different ways to think about it. And then the last one here, in terms of simplifying the roots in this question, this is going back to rules of exponents. Remember, a square root, we don't have it written, but there's a little 2 out front. There's a little 2 written right here in this little area. All right, that little 2 represents what kind of root it is. And so applying rules of exponents, when I take the square root, I divide the exponents, and I divide it by that little 2. So this one is going to be x to the 5th and y to the 7th. I divide each of the exponents by 2. That's my rules of exponents. Okay? If I look at this one, it says to solve by graphing. And so I'm just going to graph each of these. If I were to graph that first one, because it's in standard form, the easiest thing to do is find the x and the y-intercept. So right here, to find the x-intercept, I plug a 0 in for y. So that gives me when I divide each side, that's a positive 3. So it's 3, 0. If I plug a 0 in for x, it gives me the y-intercept. If I solve that, that's a negative 4. So 0, negative 4. And again, that's just for this first line. Let's do the same thing for the second line. If I wanted to graph this guy, well, let me graph that line first. So this way we don't get as confused. And I can even see the slope here after I plot those 2 points. It's up 4 over 3. And I could continue that pattern. Sorry. Got some stray marks I keep trying to erase, but I'm having trouble. Up 4 over 3, so I could keep going up 4 over 3. And now if I graph the other line, once again, x and y-intercepts are the way to go. If I plug a 0 in for x, the y-intercept, let's see, is a negative 6. If I plug a 0 in for y, the x-intercept is a positive 9. And so now, once again, if I plot these, and this might be a little bit hard to plot because we're kind of off the graph a little bit. So 1, 2, 3, 4, 5, 6, 7, 8, 9 is out here somewhere, and negative 6. And so as you look at this, it might be hard to draw a nice graph for this thing. And that's because as we look at this, we're having a little bit of trouble actually seeing where this thing is in terms of it being accurate. But if we kind of think about that, whoops, I erased too much. In terms of the pattern, it's up 6 over 9, so I can see the slope up 6 over 9. Well, that's 6 over 9. I can reduce that. That's 2/3, so I could go up 2 over 3 instead. I could go up 2 over 3. Counting is very hard. 2 over 3, up 2 over 3. And now I can get a much more accurate depiction of this line. Okay? But now solving by graphing, I need to find out where these intersect. Well, it's over here somewhere. It's off the graph. So I might have to extend this a little bit. Ready? Let's see if we can extend this just a little bit. So if I extended this, it's down 4. 1, 2, 3, 4. Back 3, 1, 2, 3. That would be this point right here. And so now I'm just going point by point to see where this matches up. This one would be down 2, 1, 2, back 3, 1, 2, 3. And there it is. It's going to match up at this point right here. And so as I kind of count backwards to that point, if I identify this ordered pair, let's see, negative 6, 7, 8. So that's negative 8 for the y. And looks like negative 3 for the x. Okay, so I had to extend the graph a little bit, and this is why graphing is a little bit tricky sometimes, okay? Because one, if it's off the graph, that causes an issue. If we have fractions, it causes an issue, okay? If they're not in a good format for graphing, it causes an issue, all right? This is why we have multiple methods. Sometimes graphing isn't the best method, and for this particular example, graphing would be good if I had a larger graph, okay? So just extend that graph a little bit, see where they intersect. So for this one, the solution is negative 3, negative 8, okay? And you just leave it as an ordered pair like that. It's telling you that x equals negative 3, y equals negative 8, okay? For this one, solved by substitution. Because this first one is already solved for y, so right here, y equals this thing, it means I can replace this y with a 3 minus 2x, okay? Because y is the same as 3 minus 2x, I can replace any y's with a 3 minus 2x, and so that's what I do. In the second equation, I replace this y with a 3 minus 2x. And now I have an equation that only has x's, and that we know how to solve. I distribute. I combine like terms. And now I continue to solve. I subtract the 6 from each side. I'm going to divide each side by a -1. So I end up with x equals 5. But I'm not done yet. I still have to go back, plug that 5 in, and get my y value. So right here, y equals 3 minus 2 times 5. So y equals a -7. Okay? And then the last thing I do is I typically write this as an ordered pair, because it's just a nice, succinct way of writing it. If you left it as x equals this, y equals this, that would be fine. That would be technically right, all right? But an ordered pair gives us a nice way of writing it, okay? If I look at the next one, same kind of thing. I want to solve by substitution. So the first thing I need to identify here is, well, which of these things would be easy to get by itself? Which variable would be easy to get by itself? And so we want to look for something that maybe has a coefficient of 1, maybe doesn't have a lot around it being added or subtracted. And so the obvious choice here is this guy. It's this y right here. So I'm going to take that first equation off to the side and say, hey, let's get y by itself. Let me solve for y. So to do that, I subtract the 3x from each side. And we're just rearranging this. I'm isolating y. So I get y equals a -3x minus 4. So if y is the same as a -3x minus 4, it means I can replace y with a -3x plus 4. And so that's what I do in this second equation. I say, hey, let's replace that y. So that's 4x minus 3y, but instead of y, I'm going to replace it with a -3x plus 4 equals 1. And now I continue to solve. I distribute. I combine like terms. I add that 12 to each side. And I divide by the 13. But again, the point here is that once you do that substitution, once you plug that value in, I end up with an equation that only has x's in it, which is something we know how to do. And that's kind of the goal a lot of times with these more complicated things. I want to get back to what I already know, all right? I'm still not done. I have to plug this back in and get my y value, and I just plug it in right here. This is the easiest one to plug it into. So I plug the 1 in for x, and now that's -3 plus 4, which is a positive 1. So it looks like the ordered pair 1, 1. Okay? If I look at the next one, it says solve by elimination. Remember, elimination, we want to add the equations together and get one of the variables to go away, all right? And so to do that, we need additive inverses. If we look at this particular example, I already have added inverses in front of the y's. So I can go right to adding these together. If I add these together exactly the way they are, the x's add up to a 5x. The y's add up to 0, so they cancel out. Equals over here, this adds up to a 25. And now I continue to solve. I'm once again left with an equation that only has an x in it, that only has one variable. So I divide each side, so I get x equals a 5. But now I still have to plug this back in and find y. So I'm going to plug it into this first one, so 2 times 5. And it doesn't matter which equation you choose, okay? I'm plugging it into that first equation, and now solving for y. Subtract the 10. And that's it. Write it as an ordered pair. Okay? If I look at the next one, if I'm going to solve by elimination, see, it's not going to work out right now because, one, nothing's lined up. Like, how am I supposed to add those y's together when they're kind of scattered all over the place, all right? And two, if I were to add the x and y, they're not going to cancel anyway. So first of all, I need to rearrange this. So the first thing I'm going to do is I'm going to rearrange this thing. I'm going to say, you know what, let's take that first guy, and essentially I'm working towards standard form. xy equals constant. We just don't care about like all the nitty-gritty details of, oh, you can't have fractions, that kind of stuff, okay? So I'm going to add the 3y to each side. So that gives me a 4x plus 3y equals 7. And so now that first equation's the right format, so if I write the other equation underneath it, see how everything's lined up. That's kind of the first thing we need to do when solving by elimination. Make sure everything's lined up. X, y equals constant. But now I need additive inverses, and so I have to decide, do I want to get additive inverse in front of x or in front of y? Well, it doesn't really matter here. The y values are a little bit smaller. Maybe I'll do the x values for fun, all right? But if I want to get additive inverses here, I have to multiply this equation by something like 7, because that'll turn the coefficient of x into a 28. Well, down here, I have to multiply this guy by something like -4, because if I turned the first x into a -28, into a 28, the second x I have to turn into a -28, okay? And so that's what I do. I multiply by -4 to get a -28. So here's the result. Here's my equations now. That first equation becomes a 28x plus 21y equals 49. The second equation becomes a -28x minus 8y equals a -36, okay? And now if I add these together, those x's cancel out. That's a 0. When I add the y's together, that gives me a 13y. Over here, when I add these together, I get a 13. I divide each side, and I get y equals 1. Still not done yet. I have to plug this back in and solve for my x values and leave myself a lot of space here. Let me do it in a different color so I can see it. I'm going to take that very first equation, the 4x equals 7 minus 3 times 1. And so it's 4x equals, that's going to be 7 minus 3, which is 4. And then I would divide each side by 4. And so once again, I get x equals 1. Okay? And so let me write this answer as an ordered pair. 1, 1. Okay? If I look at this one, it says solve by the method of your choice. And so as I look at this one, I see that everything's all lined up, so I'm leaning towards elimination. I also see that I have some nice values there, the 2 and the -1. It's really easy to say, hey, you know what? I can turn the second equation, that second x, into a -2 by multiplying each side by 2. And so the first equation, I just leave it the same. I'll leave it the way it is. The second equation now becomes a -2x minus 4y equals a -6. And now I can add these up. So I add them up here. I get a 0. The y's also cancel, so I get a collective. Collectively, I get 0 on this side. On the other side, I also get 6 plus -6, which is 0. And so this is one of our special cases. I have 0 equals 0. That's a true statement, which means this is infinite solutions. Remember, our special cases are when you get a true statement, it's infinite solutions. If I had a false statement here, if all the variables canceled and I got like 0 equals 10, well, then it would be no solution, okay? So basically, this is just showing us that, hey, this is the same line twice. It's the same equation twice. So all of their ordered pairs they have in common. So there's an infinite number of very specific solutions, okay? If I look at the next one I would probably use substitution for, only because nothing's lined up. I don't know how easy it's going to be to get the things to cancel out. So I might take this first one and say, hey, you know what? Let's rearrange this. Let's solve this guy for y by subtracting that 2x from each side. I have a variable that's almost by itself. It's really easy to get by itself, so I'm going to go substitution. And really, if I've rearranged those, if I swapped the x and the y and lined everything up, it would be easy to multiply and eliminate y as well. So elimination would also be good for this one. I just decided to use substitution. And so now I plug that into the second equation, 3x minus 2y, but instead of y, I plug in the -2x plus 6. And now I simplify, I distribute. That's a plus 4x minus 12. I combine like terms. Now I'm going to add that 12 to each side. So x equals 4. Okay, I'm still not done. I have to plug it back in over here. So y equals -2 times 4 plus 6. That's a -8 plus 6, which is a -2. Okay, and again, I write my answers in ordered pair. If I look at the next one student bought 3 pens and 4 pencils for $5. Another bought 7 pens and 12 pencils for $13. How much would a student pay for 5 pencils and 4 pens? And so the first thing I need to do, I need to write an equation for each of these situations. So the first student, I'm going to call the pens x and the pencils y, just for simplicity purposes. So what they did is they have 3 times x, so 3 times the amount for each pen, plus 4 times the amount for each pencil equals $5. That's how they get their total bill, okay? The second student, same kind of thing here. It's a 7x plus 12y equals 13. And so if I want to know how much, the end result here is that I want to know how much 5 pencils and 4 pens would be, well, I need to know how much each pen and each pencil are going to cost, okay? And so right now, x is the cost of each pen and y is the cost of each pencil. I just have to solve this system of equations so that I know how much each one costs. Then I can find out what the price is going to be for specifically 5 pencils and 4 pens, okay? So let's solve this system. As I'm looking at this thing, everything's lined up pretty nicely. So I'm going to use elimination. And for this one, I definitely want to eliminate y. And the reason for that is because it's a lot easier to turn a 4 and a 12 into the same number than it is to turn the 3 and the 7. See, if I wanted to turn the 3 and 7 into the same number, I'd have to multiply the first equation by 7, and I'd have to multiply the second equation by -3, okay? But if I look at this, all I have to do for the y's is I have to multiply this first equation. If I multiply by 3, it gives me a 12. Well, I want a -12 since this guy's positive. So I just have to multiply by -3. I have to get additive inverses, and it's much easier to do with y because it's easy to turn that 4 into a -12, okay? And so it gives me this. -9x minus 12y equals a -15. And now I can add these two equations together, okay? So here that's a -2x. So the y's cancel. Over here I get a -2. And now I divide each side. So here I find that x equals a 1. So the pens are $1 each. I still have to plug this back in and get the cost of the pencils. So I'll plug it into this first one. So from here I solve. I've got to subtract that 3 from each side. And divide by the 4. And don't be fooled here. It is 2 divided by 4, not 4 divided by 2. So that is a 1/2. Although in this context, writing a 1/2 doesn't make much sense here. It's much better to write this as 0.5. Because again, we're talking about money. We're now saying that, hey, the pens cost $1 each, and the pencils cost 50 cents each. Okay? Half a dollar. Okay? And that's great information, but that still doesn't quite answer the question. That's part of what I needed for the answer. Okay? But if it asks me, hey, how much is it going to run me if I buy 5 pencils and 4 pens? Well, let's find out. 5 pencils, those are 50 cents each. Plus 4 pens, those are $1 each. Well, let's see what we get here. Let's see, that's $2.50 for the pencils, plus $4 for the pens. It looks like I'm looking at $6.50. So do make sure that you answer the question. Yes, we needed to know the price of each, but we needed to know that so I could calculate the price of 5 pencils and 4 pens. Okay?